Hi guys, welcome back to the channel Tech Concept with May. If you remember in our last video, we dwelt on table creation within the PostgreSQL environment using our terminal. Now we need to note that our tables do not exist in isolation. Our tables share relationships with other tables. And so for that reason, we will be focusing on the relationships that exist between tables and some rules that guide our relationship definitions. Before I go any further, I'd like to request that you subscribe to the channel by clicking on subscribe icon that appears when you hover around the red subscription watermark at the bottom right of the screen. Also, I'd like to request that you hit the notification icon so that you can become aware or you can be notified whenever new videos are uploaded. That being said, in this topic, or for this part of our table creation, we're going to be focusing on relational models as references for relationship creation between database tables. So, with the concept of relational databases, a created table does not exist in isolation. Typically, the created table will be connected to one or more other tables through a defined relationship. Now, these defined relationships strengthen the integrity of stored data. The defined relationships aid better organization of data, and the defined relationships promote efficient use of database space. Defined relationships are commonly conceptualized through data models. And one common data model type that is used to depict how data elements in one table relate to data elements in another table is the entity relationship model. Now, our entity relationship model presents a simplified conception of the prospective relationships that will exist among tables or entities. Now, let's have a brief preamble to how the entity relationship models work. With entity relationship models, we need to note that our tables which epitomize entities are constructed with intent to collect pieces of information on a number of attributes in a uniform manner across many instances of the said entity. So essentially, an entity is an existing concept. It could relate to a real world object. It could relate to a human being representation. It could relate to an idea about which information can be collected. For instance, student is an entity. Now, each entity consists of attributes or characteristics that are common to the instances of the said entity. Let's look at this example. We have an entity called student. Now, the student entity may consist of the following attributes: student identification number, denoted by student ID, first name, last name, address, program enrolled for. Now, a created table that represents this entity will therefore store many instances of these attributes that correspond to records of many students. The implemented student entity will be represented like the illustration depicted below. Here you will note we have attributes of the student entity for a number of instances. Here we have 3 instances of the student entity. These instances will be scaled to records of instances that get into the millions or more. However, this will be dependent on the storage capacity of your digital device. Now, typically, an entity may share a relationship with one or more entities. For instance, the entity student may share a relationship with an entity called courses. Very often, the relationship dynamic between entities of a relational database are represented as verb terms, e.g., action words that depict how the entities relate to each other. So here we have a number of examples. We have our entities which share a relationship. A student enrolls in a program. 2 entities that share a relationship. A customer operates a bank account. Again, 2 entities that share a relationship. Also, a lecturer teaches a course. You will note that with these examples, our relationships are defined as verb terms. And so oftentimes, you will observe that relationships between entities are defined as verb terms. Also very important to note is the fact that with relational databases, we operationalize relationships in one of three ways. These include a one-to-one relationship, a one-to-many relationship, and a many-to-many relationship. Our one-to-one relationship is symbolized as follows. There will be a line that connects the two entities together, and across the lines, we're going to have two dashes that cross the lines that connect our two entities. The two dashes across the line that connects our two entities represents the one-to-one relationship symbols. With our one-to-many relationship, on one side, which is considered to be the many side of the relationship, we have a crow's foot. And on the other side, we have the dash that runs across the line which connects the two entities to represent the one side of the relationship. With a many-to-many relationship, we will note that on both sides of the line that connects the two entities, we have crow foot representations to denote the many-to-many relationship. Now, we have an ERM, or entity relationship model rule for interpreting relationships. In interpreting each option of our relationships, we read the dynamic both ways. For instance, with a one-to-one relationship between a customer entity and a bank account entity, we will read the relationship as follows. A customer can operate at most one bank account. And on the flip side, a bank account can be operated by at most one customer. This example illustrates a one-to-many relationship. Here, a customer can make many orders when shopping. However, a single order can belong to only one customer. And this illustration shows us an example of a many-to-many relationship. Here, a student can take many courses, but also a single course can be taken by many students. Now, there's something we need to note with respect to our one-to-one relationship. It's not used very often. The logic behind the rare use of the one-to-one relationship is that if the relationship possessed by two entities is only one instance of the first entity relating to only one instance of the second entity, then all of the attributes in the second entity might as well be placed in the first entity, hence eliminating the need for the second entity. This diagram demonstrates this example. Here we have a customer entity and a bank account entity, both possessing 3 attributes each. The thinking with eliminating a second entity with respect to this relationship is that all the attributes of the bank account entity might as well be placed in the customer entity, considering that the relationship is one-to-one in nature. There are some people who, however, advocate for having 2 entities, even with a one-to-one relationship scenario. These advocates believe that in order to store some sensitive information about a particular entity, perhaps a second entity may be required. For instance, in this case, account balance is somewhat considered to be sensitive information, and as such, everybody who will be privy to a customer's detail should not all be privy to the account balance of that customer. As such, if only a select few people should be privy to the account balance, such an attribute should be put or stored in a separate entity, like the bank account entity. It's also important to note that we do not represent our many-to-many relationship in its original form. With respect to entities that possess a many-to-many relationship, it is mandatory to make some necessary modification. Now, this modification will reflect in how a many-to-many relationship is represented for implementation in the database. The issue is that representing a many-to-many relationship in its original form will produce certain anomalies that will create data redundancy as well as negatively influence data integrity. Let's take this example where we have a many-to-many relationship between a student table and a course table. Now, with this example, noting that each student can take multiple courses, we will have to have an attribute in the student table to account for the courses that they will be taking. In this instance, the multiple courses that they may be taking. So we will have our table represented this way, specifically the student table, which is what we're using for the example. So here you will note that Anna Jones is taking all 3 courses that are present in the course table. As such, we will use multiple rows to store information about Anna Jones. The issue is that with this replication and storage of redundant information, we may run into integrity challenges. Take, for instance, that Anna Jones gets married and as such changes her last name to Anna Law. This change in name and as such change in rows of information storing information for Anna Jones will constitute redundant changes to the database. And these redundant changes may result in integrity issues where we make a mistake while updating one of the records. So for this reason, it's not advised that we represent our many-to-many relationship in this way. As such, whenever you see a many-to-many relationship, note that some modification must be made. We would rather represent our many-to-many relationship in this way. Obviously, we will have our two entities which share a many-to-many relationship. However, we will also have an intersection table. Notably, each of our tables must have a primary key, which uniquely identifies each record in that table. So for our student table, our student ID will constitute the primary key. And for our courses table, the course ID will represent the primary key, as these values will be unique for each record entered into these tables. Now, our intersection table is going to hold the primary keys of the student table and the course table. However, these will be noted as foreign keys to the respective tables. So student ID here will be a foreign key to the primary key in this table. And course ID here will be a foreign key to the primary key in this table. The other thing to note is with our intersection table, we're going to have two one-to-many relationships to represent the many-to-many relationship between both tables. This means from the student table to the intersection table, which is titled or called student courses, we're going to have a one-to-many relationship. And in like manner, from the courses table to the student courses table or the intersection table, we're going to have a one-to-many relationship. Now, it's also important that we note a few things with respect to the example that we have provided. Where we represent our many-to-many relationship with an intersection table included, then we can eliminate or drastically reduce the redundancy challenge that we had dealt with in the previous slide, where our many-to-many relationship was represented in its original form. Take this example here, where student courses holds information about student IDs and the corresponding courses that they are taking. Where we need to make changes to particular information in student table, we will do that just once. Noting that any replications are held in the student courses table. So in this instance, if Anna Jones got married, as had been suggested previously, and her name is changed to Anna Law, we will make that change just once, as opposed to having many replications of Anna Law in the student table. So that deals with redundancy, and as such improves our chances of maintaining integrity. The other thing to note is that with respect to any one-to-many relationship between two tables, the primary key will be held in the table that's on the one side of the relationship, as can be seen in this instance. Because the one side of the relationship is next to the student table, therefore, the primary key with respect to these two tables will be noted in the student table, whereas the foreign key for this relationship between these two tables will be noted in the student courses table. In like manner, with the one-to-many relationship between the course table and student courses table, you will note that the primary key is noted where the one side of the relationship is denoted, which is the course table, whereas the foreign key is housed in the student courses table, where the crow's foot is denoted. Notably, if we keep this rule in mind, we will have very little confusion when modeling relationships, especially one-to-many relationships or many-to-many relationships. Now, with a relational model, we may have a lot more entities represented, and this will be based on our requirements elicitation at the beginning stages of the database creation exercise or project. So that being said, we're going to stop the video here, but I also want to implore you to do some studying on database normalization, as this will help you to derive better insight about the rules that guide the composition of our database tables. And when we talk about decomposition, we're basically talking about the breaking down of tables into smaller tables, okay, or separating the attributes that exist in a single table. So that being said, we're going to end this video here. Please do not forget to subscribe as well as click the notification icon. In our next video, we will be implementing the relationship that exists between two tables that possess a one-to-many relationship for demonstration's sake, so that you become aware of how to implement these relationships in a database. So see you in the next video. Bye.